Welcome to today's Explainer, where we're digging into a seriously fascinating chapter called We Distribute, Yet Things Multiply. You know, a lot of people look at algebra and just see this rigid, kind of scary set of abstract rules to memorize. But today, we're going to reframe that entirely. We're looking at algebra as this beautiful language of patterns. It's basically a tool that takes the everyday arithmetic we already know and gives us these incredible, practical shortcuts.
To show you exactly what I mean, let's kick things off with a little magic trick straight from the source text's exercises. Tell me, how fast can you calculate 495 multiplied by 11 in your head? Seriously, no calculator, zero scratch pad, just mental math. For most of us, taking a 3-digit number and multiplying it by a 2-digit number, well, it takes a second, right?
But the answer is exactly 5445. Boom, just like that. And it's not a superpower. If you know the underlying algebraic pattern, you can pull that answer out of thin air almost instantly. It really highlights how incredibly fast these math shortcuts can be once you're in on the secret.
So let's peel back the curtain on this trick. Because you're multiplying by 11, there is a very specific, repeatable pattern you can exploit. Here's how it works. First, you just take the outer digits of 495, so the 4 and the 5, and you park them at the extreme ends of your answer. Then, working from right to left, you just add the adjacent digits together. So 5 plus 9 is 14. You lock in the 4, carry over the 1. Then 9 plus 4 is 13, plus that carryover of 1 makes 14. Lock in that 4, carry over the 1 to your starting digit, which bumps that initial 4 up to a 5. Smoosh it all together and you've got 5445. Honestly, it looks like absolute genius to anyone watching, but it's just pure, simple pattern recognition.
Okay, so here's our roadmap for today. Number 1, unpacking the distributive property. Number 2, expanding complex expressions. Number 3, 3 essential math identities. And finally, number 4, the power of pattern recognition.
Let's jump right into part 1, unpacking the distributive property.
Getting a grip on this definition is absolutely crucial. Distributivity is, at its core, simply a property that connects multiplication and addition. Algebraically, it's written out as A times the quantity B plus C equals A times B plus A times C. And remember, in algebra, we usually skip writing the little x for multiplication before or after brackets. If you see a letter huddled right up next to parentheses, it means multiply. You're essentially taking that A on the outside and distributing it to the B and the C on the inside.
And this is where it gets cool, because it proves algebra isn't some alien, disconnected concept. It's totally rooted in everyday logic. Think about a standard arithmetic problem, say 23 times the quantity 27 plus 1. Now compare that to its algebraic equivalent. If you wanted to know exactly how a product jumps up when you add 1 to a number, you don't have to sit there and guess. The algebra literally proves it for you. If you swap A for 23, B for 27, and C for 1, you instantly see that the final product goes up by exactly A, which in this case is 23. Algebra is really just generalizing the math you've been doing your whole life so you can apply it universally.
All right, moving right along to section 2, expanding complex expressions.
Now what happens when things get a bit more crowded? Here's the general form for finding the product of two expressions that each have two terms. The quantity A plus B multiplied by the quantity C plus D equals AC plus AD plus BC plus BD. Basically, every single term in the first bracket has to multiply by every single term in the second bracket. It's like a big handshake line where everyone meets everyone. But why does it work that way? We're definitely not just going to take this on faith.
The source material breaks this down beautifully, showing the intermediate logical steps that prove exactly how these expansions work. It's a lot like peeling back the layers of an onion. First, you start with an expression like A plus B, all multiplied by C. Next, you apply the commutativity of multiplication. That's just a fancy way of saying order doesn't matter, so we can legally flip it around to C times A plus B. Then we use the distributivity rule we just talked about, turning that into CA plus CB. And finally, we hit it with commutativity one more time to get AC plus BC. The big takeaway here, these supposedly complex algebraic rules, they're really just a chain of super simple, undeniably true logical steps.
Let's dive into section 3, 3 essential math identities.
Now these 3 right here are the real game changers. It's fascinating how neatly these essential identities stack up for incredibly easy pattern recognition. We've got the square of a binomial with a plus, the square of a binomial with a minus, and the product of a sum and a difference. You could totally use the long-form expansion we just walked through to prove every single one of these. But the reason this matters so much is that once you recognize these specific patterns, you never have to calculate them from scratch ever again. You literally just plug your numbers right into the expanded form. It saves a massive amount of time and mental energy.
Let's ground this back in reality with a quick example. Check out this physical number pattern from the source text. 9 times 9 minus 1 times 1 equals 10 times 8. Now, if you crunch the numbers normally, 81 minus 1 is 80, and 10 times 8 is 80, so obviously it works. But look at it through the lens of that third algebraic identity we just mentioned. A squared minus b squared equals the quantity a plus b times the quantity a minus b. The arithmetic matches the algebra perfectly. Your a is 9, your b is 1, so 9 plus 1 is 10, and 9 minus 1 is 8. The algebra perfectly justifies the numerical trick. It's brilliant.
And that brings us to Section 4, the power of pattern recognition.
This is a fantastic line in the text that says, algebra makes use of letter symbols to write general statements about patterns and relations in a compact manner. I really want to echo that core philosophy. Algebra is absolutely not about inventing new, confusing math just to torture us. It is simply a highly efficient, compact shorthand for the logical truths that already govern the universe. It's literally just a way of writing down the underlying rhythm of numbers. So, summing up the big picture from the chapter today. First off, algebra is the ultimate tool for justifying mathematical conjectures. You don't have to sit there wondering if a trick works for every single number in existence. Algebra proves for a fact that it does. Secondly, there are almost always multiple ways to tackle a problem. You can grind out the long arithmetic, you can draw a geometric diagram, which the text actually dives into as well, or you can leverage these algebraic identities. And lastly, because of all this flexibility, finding different ways to approach the same problem is fundamentally a deeply creative process. Math isn't just cold calculation, it's creative problem solving.
Which brings us to the end of today's explainer. But the text leaves us with this brilliant little challenge to really test out your new pattern recognition skills. Think about everything we covered. If you take the quantity a minus b and cube it, do you start to see a pattern emerge? Based on the squares we unpacked today, what do you think the next identity in that sequence would actually look like? Grab a piece of paper, test it out for yourself, and see if you can be the one to uncover the underlying rule. Thanks so much for joining me for this explainer, and keep looking out for those patterns. Catch you next time.